Hello everyone. Welcome back to Tech Adventure. I hope you're doing great in your journey through software development, embedded systems, and interview preparation. So far, we've covered protocols, microcontroller peripherals, Vertex concepts, C and C++ interview preparation, solid principles, and design patterns. Recently, we started our AI series, exploring AI, ML, DL, LLMs, model context protocol, and edge devices. Today, we continue that journey with one of the most exciting topics in tech: CPU, GPU, FPGA, and ASICs. The processing engines that power everything from smartphones and IoT devices to autonomous cars and AI systems. We'll explore what they are, how they differ, and why they matter in modern embedded systems. Let's dive in.
Welcome to the Deep Dive. Today, we are really getting into the silicon guts of modern tech. We're looking at those four foundational processors: CPU, GPU, FPGA, and ASIC.
Right.
And not just defining them, but trying to understand the really tough, sometimes costly trade-offs engineers face when picking the hardware that, runs everything. Your phone, an autonomous car, everything.
Yeah, and these choices they're monumental. The sources we've looked at, drawn from these high-level interviews with architects and embedded systems AI roles, they show that picking the right silicon, it's often a huge commitment, millions of dollars sometimes.
And it's tied directly to real-world physics, isn't it?
Yeah.
Latency, power draw, how many you're making, how adaptable it needs to be.
Exactly. All those constraints.
Absolutely. So the mission today is to get past just the Wikipedia definitions. We want to understand the actual requirements that push a designer towards, say, an FPGA instead of a GPU, and ultimately kind of find that crucial line separating a system that's super flexible from one that's just purely optimized for speed and efficiency.
It really is the art of compromise, isn't it? We're going to show you why in modern computing, you often can't just pick one winner. You need all four working together in what we call a heterogeneous system.
Okay, let's dive in. Let's unpack this, starting with the one most people know best, the CPU, the central processing unit, kind of the flexible brain running the show.
Yeah, the CPU is your generalist. It's the sequential mastermind. It's really optimized for running the operating system, handling control logic, making those complex single-thread decisions.
So if you're writing standard code, C++ and G, that kind of thing, you're usually aiming for the CPU.
Generally, yes. It gives you maximum flexibility. It can do almost anything. Maybe not the fastest at everything, but it can tackle it. Think of like a basic microcontroller, an STM32, handling simple control tasks in an IoT gadget.
Okay. And then we swing completely the other way to the GPU, the graphics processing unit, which, it's totally transformed AI and data processing.
Totally. The GPU is a parallel powerhouse. So instead of having a few very complex cores for sequential tasks, it's got thousands of smaller, simpler cores.
Right.
And its architecture is designed for something called SIMD, single instruction, multiple data, which basically means it's amazing at highly repetitive data parallel jobs.
Like churning through huge matrix multiplications.
Yeah.
The kind you need for AI training or complex computer vision.
Exactly that. It's the difference between having one really smart manager, that's the CPU, versus a whole factory floor packed with thousands of workers doing the same repetitive task very fast. That's the GPU.
Good analogy. Like those NVIDIA Jetson boards you see in robots and drones doing real-time object detection. That's a classic embedded GPU example.
Perfect example. Okay, but now we get into something quite different. The FPGA, Field Programmable Gate Array, this one. It really changes how processing even works.
Yeah, this is where my brain starts to bend a little. It's got programmable in the name, but it's not software. It's hardware logic.
Right. That's the key. The FPGA is the reconfigurable customizer. Instead of executing sequential software instructions, you are literally programming the logic gates themselves, the connections between them, after the chip's been made.
Wow.
So the task you design runs in parallel inherently because you're creating a dedicated hardware path just for that calculation. And the payoff is ultra low latency for specific things like, say, digital signal processing.
Okay, that flexibility sounds incredible. You can update the hardware logic out in the field. But I always hear the learning curve is just brutal. Why is FPGA programming so much harder than, writing some C++ hell?
It's a completely different way of thinking, a totally different paradigm. You're not writing a sequence of steps for a processor to follow. You are describing a physical circuit. You have to use hardware description languages, HDL, like Verilog or VHDL.
Yeah.
And if you describe that circuit incorrectly, maybe get the timing wrong, you introduce instability. You have to think parallel hardware processes all running at once, not just step-by-step software. That complexity, it's a major barrier for many teams.
Okay, that makes sense. And then finally, the fourth cornerstone, the ultimate fixed function performer, the ASIC, application-specific integrated circuit.
The ASIC is, well, it's fixed perfection in a way. It's custom-built from the silicon wafer up for one single job. One application.
And once it's made,
that's it. It's permanent, can't be reprogrammed. But because it's perfectly optimized, absolutely tailored for its one task, it achieves the highest performance per watt, the lowest power consumption, usually the smallest physical size, too.
But the downsides are huge, right?
Yeah.
Zero flexibility. And I hear the upfront cost is astronomical.
Exactly. Astronomical NRE, non-recurring engineering costs. You only really see ASICs in mass market devices where they make millions, like the Apple A series chips and iPhones.
Got it. Okay, so we've defined the four corners. Now for the real deep dive, the trade-offs. Let's start with something the interviews kept bringing up, the latency war. If a GPU is this parallel powerhouse, why would an engineer ever choose an FPGA for speed instead?
This is such a critical distinction. It's about the nature of the speed. See, the GPU offers fantastic throughput. It can process enormous amounts of data very quickly, in total, aggregate speed.
Okay.
But because it achieves that by batching data, managing thousands of threads, shuffling things around, the time it takes for one specific piece of data to get all the way through the system is, well, it's non-deterministic.
Non-deterministic.
Yeah.
Meaning you can't guarantee it'll happen in, say, 50 microseconds every time.
Precisely. It might average 50 microseconds, but sometimes it could be 100, sometimes 30. You don't have that absolute guarantee.
And if I'm the architect designing, I don't know, an automotive safety system, like emergency braking, or a high-frequency trading platform, that unpredictable delay, that could be catastrophic, literally fatal or financially ruinous.
Exactly. Those systems demand deterministic latency. They absolutely require the guarantee that the response will happen within a specific tight timing window, maybe microseconds every single time, without fail.
And the FPGA delivers that.
Yes, because its logic path is essentially a fixed hardware circuit implementation for that task. It guarantees that real-time, predictable response. That's why FPGAs are often mandatory for critical signal processing. Think 5G base stations processing radio signals or automotive radar systems.
That distinction, throughput versus predictable, deterministic latency, that's absolute gold. Yeah. Okay, so let's use the autonomous car as the ultimate example. We need all these parts, right? So the GPU is doing the heavy lifting on deep learning object detection, and the CPU is managing the overall driving decisions. Where does that low latency deterministic FPGA fit?
It often fits right at the edge, close to the sensors. Imagine the raw data flooding in from LiDAR or radar sensors. That data stream might need ultra-fast processing, filtering, maybe some specific digital signal processing before it even gets passed to the GPU for the complex AI recognition.
So the FPGA does that initial time-critical pre-processing.
Exactly. It handles that immediate deterministic work. Then the cleaned up, maybe partially processed data goes to the GPU for recognition. The GPU figures out that's a pedestrian. Then the CPU gets that information and decides, okay, apply the brakes. It's a pipeline, a chain of specialized components, each doing what they do best.
That makes perfect sense. A real heterogeneous system in action.
Yeah.
Okay, now let's shift to the big financial trade-off. The battle between the FPGA and the ASIC. If FPGAs are so flexible, reprogrammable, updatable in the field, why on earth would a company swallow that massive upfront cost and inflexibility of an ASIC?
Yeah, it comes down to two things mainly. Scale, and that huge financial hurdle we mentioned. NRE, the non-recurring engineering costs.
Right.
designing an ASIC, getting the mask made, fabricating it, that costs millions of dollars up front. And the design cycle is long, easily a year, maybe two. So if you only plan to sell, say, 10,000 units of your product,
That NRE cost spread over just 10,000 units makes each chip incredibly expensive.
prohibitively expensive usually. The FPGA, while maybe more expensive per chip initially than an ASIC could be at volume, has virtually zero NRE. You just buy the FPGA and program it.
But once I know I'm going to ship millions of units, like in a smartphone,
Now the equation flips entirely. Once you hit mass production millions, tens of millions, the ASIC absolutely crushes the competition on per unit cost.
and not just cost, right?
Yeah,
Power and size, too.
definitely. It becomes the cheapest, the smallest, and the most power-efficient option per unit. You have to remember, FPGAs are inherently somewhat inefficient from a power and size perspective. All that reconfigurable logic fabric, even the parts you aren't actively using for your design still take up physical space on the chip and consume some power.
Right. It's like having a huge box of Lego bricks, even if you only needed half of them. They're still in the box.
Good analogy. Whereas the ASIC is custom-built with only the logic needed for its specific task. No waste.
And that ruthless efficiency is paramount in something like a smartphone. The sources really hit on this. ASICs are basically mandatory there, not just for cost, but to stay within the thermal limits and maximize battery life.
Exactly. You need that absolute best power-to-performance ratio. You just can't afford to put a relatively large, power-hungry FPGA in a tiny, battery-powered handheld device if an ASIC alternative exists. That's why phones have dedicated ASICs for things like the camera's image signal processor, ISP, or specialized AI neural engines. They do those fixed tasks with incredible precision and minimal power draw.
So it sounds like the ASIC is often the ultimate destination for high-volume products, but the FPGA plays a crucial role in actually getting there, like a travel guide.
That's a great way to put it. It's the classic prototyping path. When engineers are developing something complex and new, maybe a brand new 5G radio protocol or some novel AI accelerator architecture, they almost always start with FPGAs.
Because they can change things quickly.
Exactly. FPGAs allow for rapid iteration. Test the design, find bugs, fix the logic, reprogram it maybe in hours or days. You don't have to wait a year and spend millions for a new silicon spin like you would with an ASIC revision.
Okay.
So you use the FPGA to prove out the concept, stabilize the design, make sure the standard works. Then, once everything is locked down, validated, and ready for mass deployment, then you commit the resources to create the highly efficient fixed-function ASIC for the commercial rollout. The FPGA de-risks the massive ASIC investment.
Makes sense. Okay, let's pivot slightly and look at the partnership that forms the backbone of almost every modern computer, from laptops to supercomputers.
Yeah.
Heterogeneous computing, usually meaning the CPU and GPU working together.
Yeah, this is probably the most common pairing people encounter. They complement each other almost perfectly because they're designed for such different kinds of work.
How so?
Well, the CPU, as we said, excels at sequential tasks. It manages the operating system, handles networking, deals with complex control flow, makes decisions. It's the conductor, the manager. The GPU, on the other hand, is that specialized math accelerator. It handles the parallel grunt work, transforming huge amounts of data simultaneously, like rendering graphics or running AI models. It doesn't manage much. It just calculates incredibly fast in parallel.
So let's take a practical example, like a sophisticated camera drone. How would the CPU and GPU split the work?
Okay, good one. The CPU would likely handle the core flight control, managing the motors, executing the navigation waypoints, maintaining stability based on sensor inputs like the IMU. That's all sequential control logic.
Makes sense.
Meanwhile, the GPU would take the high-resolution video stream from the drone's camera and run, say, complex object detection and tracking algorithms, or maybe algorithms for obstacle avoidance based on that visual data.
So the CPU flies the drone, the GPU sees for the drone.
Pretty much. It's a perfect division of labor. You leverage the CPU's strength in control and decision-making, and the GPU's strength in massive parallel computation. Together, they achieve much more than either could alone.
Okay, this is bringing everything together nicely. We have the players, we understand the key trade-offs like latency and NRE cost. So now let's try to build the final decision matrix. When an engineer stares at a new project, how do they boil it down based on power, cost, and maybe longevity? Let's summarize the best fit for some core applications.
Okay, let's categorize by the dominant requirement.
Yeah.
Say you're building millions of tiny, cheap, battery-powered IoT sensors. They just need to wake up occasionally, maybe read a sensor, transmit a small amount of data, and run some simple logic. What do you choose?
Got to be the CPU, right? A simple, low-cost microcontroller. Power is minimal, tasks are general.
Exactly. Low cost, low power, general-purpose tasks point to the CPU. Okay, next. I'm a huge tech company. I'm building a massive data center to train the next generation of large language models. Performance is everything. Cost is secondary. Power. Well, I have a power plant nearby.
That screams GPU. High powers is okay. You need that massive parallel throughput for training.
Correct. Massive throughput, high power budget leads you to the GPU. Right. Different need. I'm designing high reliability automotive radar. Or maybe critical telecom infrastructure like a 5G base station component. I need guaranteed sub-millisecond response times. Latency must be absolutely predictable.
That's the deterministic latency requirement we talked about. That points squarely at the FPGA.
Precisely. Real-time, low deterministic latency is the FPGA's sweet spot. And finally, I'm designing a main processor for the next iPhone. I know I'm going to make 100 million of them. It needs to be incredibly powerful, sip battery power, and fit in a tiny space. The functions are well-defined, run the OS, handle the camera, accelerate AI.
That's the mass market high efficiency play. You bite the NRE bullet and go for the custom designed optimized ASIC.
You got it. Best performance per watt, lowest cost at extreme volume, smallest size, that's the ASIC.
Okay, that maps it out pretty well. But that brings us to one last really critical consideration you mentioned, future-proofing. Which of these is more adaptable, more future-proof?
Yeah, that's a big one, especially when standards might evolve.
Based on everything we've discussed, the FPGA seems like the obvious winner here, doesn't it? Because it's reprogrammable.
Hands down, yes. Because the FPGA's logic can be reconfigured in the field via a software update, essentially, it is inherently more future-proof against changing requirements or evolving standards.
So like if a new encryption algorithm becomes mandatory or a 5G protocol gets an update.
You can potentially update the FPGA logic to support it. An ASIC, designed and fabricated today for a specific fixed standard, well, the moment that standard changes significantly, that ASIC might become partially or wholly obsolete. It has zero flexibility.
You can actually see that exact evolution play out really clearly in one specific area.
Yeah.
Cryptocurrency mining. It perfectly tracked this trade-off between flexibility and optimization.
Oh, that's a fantastic real-world example. It's like a microcosm of this whole deep dive. Mining started out being profitable on standard CPUs, then quickly moved to GPUs because they offered much better parallel processing power for the hashing algorithms. And they were flexible that you could switch algorithms.
Right, early days.
Then, as the mining difficulty skyrocketed, people needed more efficiency. So miners started designing custom hashing algorithms implemented on FPGAs. Better performance per watt than GPUs, still somewhat flexible if the dominant algorithm changed.
But still not the ultimate optimization.
Exactly. So the final step, once specific algorithms like Bitcoin's SHA-256 became totally dominant and stable, was the move to ASICs. Purpose-built mining ASICs sacrificed all flexibility but offered the absolute maximum hash rate per watt. Non-negotiable optimization became the only way to stay competitive. That journey perfectly shows the progression. Trading flexibility for efficiency as requirements solidified and scale increased.
Wow, that really crystallizes it. So the choice between CPU, GPU, FPGA, and ASIC, it's never arbitrary, is it? It's always a very precise engineering calculation. You're balancing performance needs against the upfront cost, the power budget, the physical size, and that crucial need for flexibility versus optimization, all dictated by the specific demands of that embedded system.
Absolutely. And really understanding these distinct roles, how they complement each other, how they trade off against one another, that's the key to tackling complex modern engineering challenges. You're always deciding where to place your bets on the generalist brain, the parallel math army, the reconfigurable custom hardware, or the ultimate fixed function speed demon.
Okay, so here's a final provocative thought for you, our listener, to chew on. If ASICs offer the highest performance, the smallest size, and the absolute best power efficiency, why haven't we just eliminated the other three?
Yeah.
Why not just build a specialized ASIC for every single function in a computer?
Yeah, think about that. Think about the millions in NRE, the years it takes to design just one fixed piece of silicon, and what happens the moment requirements change, even slightly. That might just tell you why we still desperately need those flexible CPUs, those powerful GPUs, and those adaptable FPGAs.
Indeed. Well, that's all the time we have for this deep dive. Thank you for joining us.
Thank you for watching. Please like, share, and subscribe to our channel for more exciting updates. Your support motivates us to create valuable content. Share your feedback or topic requests in the comments. See you in the next deep dive learning or interview session.